Nobody showed up.
Still early.
Oh, really?
Still got 8 minutes. Hey,
He goes, I'm burning a little bit now. Alright, cover. Yeah. 2,000 at least on that. There's- That's your guide. That is a formula. Average flow. He's like, I don't even know. Honestly, that- You might just know. But, you know. Watch this thing, I go, but. We get a block. You Not gonna $18,000. Right now, it's 30 grand. Put it in like 16. They're so rare. Which one? MJ55. See the pages. Carol? I'm good. Be on average like 30, 40 grand on these. Nothing to restrict out. Question. Basically, sending it from where the corporation. All of the files, it's like you like the exams, you like actually like the recs, like for like exact, so you like exactly. Yeah, do that. But like Stephen will have like, I don't think so. I'm gonna check. Maybe it sounds stupid, but like it's just that she so like nonchalantly and like the rest. Yeah, exactly. It's necessary to like. Yeah. Warm it up. Your other fan jobs and then probably one screen as well. Got it, like they do. This was in his actual. I'm pretty sure they have the budget's $50 like mass, so. Yeah. I don't sort of, I don't have. That's the only one that's not pretty fast. The sharpest one.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, staying dry, hopefully. It's rained a lot this morning. You guys are staying safe, drive carefully on the freeway. I saw a lot of accidents today on the way here, so make sure you guys are driving safe. Okay, so the plan for today is we're going to continue where we left off. I think we just started talking about Navier-Stokes last time. So we'll solve for a solution to Navier-Stokes today, so that'll be exciting. And then we'll relate it to blood flow through something called Murray's law. So that's hoping that's where we're going to end up today. Okay, so some announcements. So remember your introduction email assignment that is due tomorrow. So if you haven't sent me an email yet, just introducing yourself, please do so. Make sure you get it in before the deadline so I can give you credit for it. And the first homework assignment besides that has been posted. So hopefully you guys saw that this morning. It's mostly, for the most part, conceptual questions since we haven't really gone over anything else except for concepts. And so make sure you take a look at that because yeah, there's a lot to go over with especially with the anatomy stuff we did last week. Okay. All right. I think that's all my announcements. Are there any questions I can answer before we get started for today?
Participation.
Yeah, it's completion. Yes. But I do, I saw this a lot last semester. So, you have to do more than just write the question down. Like you have to actually give it an attempt to solve the problem. Yeah. I'm not grading for correctness, just for completeness. Yeah. All right, so let's go to get started. All right, so first thing I'm gonna do, actually, I'm gonna scroll up here a little bit. Let me just kind of come back to where we were on Tuesday. Okay, let me kind of erase all these rainbow lines here. Okay, so what I have here with all the colored circles and everything, this is our Navier-Stokes equation. So this is the conservation of momentum in for fluids. And so the idea is that if you can solve this equation, right, and the unknowns in this equation are your velocities, so these are these things right here, all these u values, okay. If you could solve this equation for those u's, you can obtain a lot of information about about your flow in general, because you can differentiate it, get the shear stress, you can integrate it, get the flow rate, okay. And so that's what we're going to be doing today. So we're going to be tackling this giant equation, and we're going to be solving. Okay. So the last thing we did on Tuesday was we talked about this equation, and we mostly talked about it from the perspective of looking at all the different terms and the groups of terms that we have in here, and kind of talking a little bit about what they represent for fluid flow. Okay. So we have things like the unsteady term, that's our time derivative. We have the convective terms, we have the pressure term, gravity, and the viscous terms. Okay. And so what we're going to do today is typically when you have like a very complicated partial differential equation like this, you can't really solve this straight up. And so you need to simplify this equation and get it to a form that is easier to solve. And the way that we're going to do that is by applying assumptions. So that's the first thing we're going to do today, talk about the assumptions. We'll talk about which assumptions are typically valid in blood flow, and what effects they have on the Navier-Stokes equations. Then we'll actually go about solving these equations. Okay, so let's go ahead and get started with that. Let's go with assumptions in pink. All right, so we're going to talk about the common assumptions that we're going to make for blood flow. So some of these will be generally applicable for all types of blood flow. Some of these are a little bit more of a stretch, considering some of the aspects of blood flow that we know about already. But we have to make all of these assumptions just so that we can solve our equation. Okay. So we will use So we're going to use these assumptions to just cancel the terms in Navier-Stokes equations, just so that we can solve the equation. Because right now, as it is, we're not able to solve Navier-Stokes. Okay, so we have five assumptions here. All right, number one is going to be the steady state assumption. So under the steady state assumption, we're going to assume that our flow does not depend on time. So we have no time dependence. Okay. Mathematically, what this means is that whenever we have a derivative that involves time, we can go ahead and set that equal to 0. Okay, so partial t, we set that equal to 0. Okay. So we only have one unsteady term in Navier-Stokes. It's just the very first term, the partial u partial t. So under this assumption, we're going to set that equal to 0. Okay. This is a pretty standard assumption for your previous fluids classes. just because analyzing unsteady problems is very difficult, even at the graduate level. But we kind of know already that this is something that's not valid in general for fluid flow, okay? Or blood flow, excuse me. Okay. And remember, the reason for that is because of the action of the heart, because the heart has to pump and then relax, pump and then relax. This is an unsteady process, and it's going to lead to spikes and valleys of the flow rate. Okay. So we're going to need different tools to analyze these unsteady situations, but we'll kind of work our way up to there for the rest of the class. But for now, our goal is just to get the simplest solution to Navier-Stokes that we can, and usually that involves assuming steady state. Okay. All right, number two. Number two is the incompressible assumption. All right, so under the incompressible assumption, we assume that blood acts like an incompressible fluid, okay? So that ultimately what that means is that we're going to assume the density is constant. Okay. Basically, what that means is that if you have a fixed volume of blood, and you can try to squeeze it as much as you can, that blood it's still going to be the same volume, right? So it's unable to be compressed. And my iPad is lagging. All right. So actually, this assumption that we have here, the incompressible assumption, we've already kind of assumed it. And the main place where this shows up is in the continuity equation, in the conservation of mass. Okay. So if you recall, from last time, our conservation of mass took a fairly simple form. It was just three partial derivatives just added to each other. And so that form of conservation of mass is only possible under the incompressible assumption. Okay. You'll catch up eventually, I hope. There he goes. Okay. Yeah, so incompressibility, we assume the blood density is constant. Okay. Okay. Number three. The number three assumption that we're going to make is called 1D flow. My iPad's literally like 30 seconds in the past. There we go. Okay. You just have to make fun of it and then it catches up. Okay. So under the 1D flow assumption, normally velocity is a vector quantity, right? So it has components in all three spatial dimensions. But in 1D flow, we are going to assume that two of the spatial dimensions of velocity are going to be zero. Okay. And so we're going to assume the velocity vector has only one component. All other components are zero. All right, so this is kind of an interesting one for blood flow because blood flow, remember, takes place in a tube. Okay. So generally speaking, we're going to be using cylindrical coordinates for our Navier-Stokes. Okay. Under the 1D flow assumption, we're going to assume that the flow only goes down axially down the vessel tube. Okay. Okay. And that direction is the z direction. Okay. The axial component being okay. Our other two components in cylindrical coordinates are the radius the radial component. Okay, so the radial component goes from the center of the vessel, it points out towards the walls. Okay, so we're going to assume that that component is 0. Okay. And the other component that I think is I think neglected a lot in cylindrical coordinates is the rotational component, and so the theta component. So that one kind of rotates around the vessel radius. Okay. And so that one, of course, is going to be 0 as well. And so basically what we're assuming is that we're not going to have any kind of swirling flow. Okay. And so if you have any kind of swirling flow, if there's a whirlpool showing up, that would, of course, manifest in the theta component. Okay. It's no swirling. And the radial component is actually very interesting. The R component, in reality, there is some radial component to the velocity, but that's mostly a result of the fact that our blood vessels are flexible. Okay. So if you can imagine if your blood vessel is inflating, okay, and so if it's getting bigger, the radius is increasing. In order for that to happen, there needs to be a component of the velocity that points towards the walls. Okay. But for our case, we're going to assume that the walls are completely rigid. And so there's no reason for the blood to kind of point towards the wall. Otherwise, it would kind of, either burst through the wall or violate conservation of mass. Okay. All right. So again, flexible walls is something we'll deal with kind of later on in the class. We don't really quite have the tools for that just yet. But that's kind of something to keep in mind. But as long as your walls are rigid, you only have one component of the velocity, which is in the axial direction. Okay, number 4. Our number 4 assumption is we're going to ignore gravity. So this one's pretty straightforward. We're just going to ignore the effects of gravity. Okay. Okay. In reality, gravity does play a factor. It does play a factor, especially when blood travels from kind of a lower point to a higher point in your body, or vice versa as well. But generally, when you compare it to the pressure forces, gravity is really small, because the thing with gravity, gravity terms or body force terms generally scale off the amount of mass that you have, right? So the more volume that you have, the more mass that you have, gravity is going to play a bigger impact. The thing with blood vessels is that they're so tiny, right? So their diameter is so small. There's just not a lot of mass in a blood vessel at any given time. And so when you compare that to the pressure forces that are generated by your heart, gravity is usually a lot less. And so when we say that we're going to ignore gravity here, it's not that we're doing this analysis on the moon or anything like that. It's just that when you compare the magnitudes compared to pressure, pressure is always going to be much greater. And so, even if we included gravity in our equation and we were to solve for the solution, it would make a very, very small difference in what we get. So just for simplicity, we can just assume it's 0. Okay. And so the last assumption that we have here is called the axisymmetric assumption. Okay. This was kind of an interesting one. And so this basically assumes that you have an axisymmetric situation. So this is the term that's used in cylindrical coordinates, basically saying that nothing changes as you rotate around the vessel wall. So there's no dependence on the solution on theta. Okay. So that means any derivatives that involve theta, we're going to set it equal to 0. Okay. All right. Any questions? Yes.
Is the axisymmetric assumption based on like a geometry? Like, let's say we had like an elliptical blood vessel, would that be not true then for?
Yeah, no, that's a good question. So if you have an elliptical blood vessel, then your radius of curvature is going to change as you go to different parts. Then that would be probably something that you would not be able to assume axisymmetry. Yeah. Yeah, part of that is because you have a constant radius of curvature as you go around a literal cylinder. Yeah.
Constant.
Yeah. Mhm. All right, any other questions on this? Okay, all right, so let's get into the solution. Okay. Did you guys solve Navier-Stokes when you took Fluid Mechanics 333? Okay, so you guys are familiar with the concept, which is good. Okay, so we're going to be solving for the solution, the kind of the standard solution of pressure-driven flow in the cylinder. Okay, so this solution is actually a famous one, and so it's so famous that it's named after the guy that found it. So it's called Hagen-Poiseuille flow, or the Hagen-Poiseuille solution. All right, so this solution right here, named after the first guys to get it, solves Navier-Stokes for steady flow in a rigid cylinder. Okay. Rigid cylinder meaning that the walls are fixed. Okay. All right, so let me go ahead and draw it. Okay, so here we have our cylinder. Okay. Oh, question, sorry.
When analyzing blood vessels, don't they expand and contract?
They do. Yeah, and that's definitely something we're going to take that into account later on. But for now, we're just going to assume a rigid tube just for simplicity. So the rigidity assumption is actually interesting because some of the smaller vessels, even though they do kind of expand and contract, the amount that they expand and contract is fairly small. So this solution is still valid for certain vessels, but for the most part, you do have flexible walls. But what we'll see later on is that this solution will be kind of our starting point for that. And then we'll kind of add in the flexible walls and we'll see how that affects the solution. Okay, so here we have our tube. Flow is going to go from left to right. We have our UZ just like that. Okay. We're going to assume our cylinder here has a length of L. Okay. Our flow is pressure driven, and so we have pressure on both sides, P1, P2. And in order to drive flow from the left to the right, P1 must be greater than P2. Okay. We're going to assume that we know the radius of this cylinder. And so the radius is going to be given by capital R. Okay. That's a fixed quantity because it's a rigid cylinder. Okay. Another thing that we're going to assume is that our pressure gradient is a constant. Okay. And so the pressure gradient, is just a change in pressure over a certain distance. Okay. And so in this case, it's going to be P1 minus P2 divided by L. Okay. If you were to take the limit of this expression as L goes to 0, so kind of the old school definition of a derivative, okay, we get dP or partial P partial Z. Okay. And so this is going to be constant. Okay. Which is a pretty reasonable assumption in rigid wall flow. Because the wall is a fixed size, the amount of pressure, the amount of energy it takes to drive the flow is kind of constant all throughout the tube. Okay. All right, and so what we're going to do is we're going to write out the Navier-Stokes equations, this time in cylindrical coordinates, and then we're going to apply all of our assumptions to simplify that equation and solve for a solution. Okay. Okay, so we're going to write out Navier-Stokes in cylindrical coordinates. So we're going to start with the continuity equation. We're going to start with conservation of mass. Okay. Okay. So this is the cylindrical version of the equation that we saw previously. Okay. So this is going to be 1 over r partial r of u times ur times r. Okay. Plus 1 over r partial theta of u theta. Okay. Plus partial z of u z. Okay. And you add all these up, and then you're going to get zeros. Okay. So this differential equation right here is an expression of conservation of mass for a fluid in cylindrical coordinates. Okay. All right, so let's simplify this. And so we have one assumption that's going to dramatically simplify this. Okay. And so if we look at our assumption for 1D flow, okay, and so under the 1D flow assumption, the only non-zero component of velocity is going to be uz. Okay. And so this first term has a ur. Okay. So the u sub r there, that's the velocity component in the radial direction. So so by our assumption, we already know this is going to be 0. Okay. And the second term has u theta. Okay. So u theta being the velocity in the rotational direction, polar direction. So we can set that equal to 0 as well. Okay. All right, and so when those two terms cancel, we're left with just a single term here. And so you get partial uz partial z is equal to 0. Okay. All right. So this right here is a pretty important result. And so what this tells us is that our flow is fully developed. Okay. And what fully developed means is that the velocity field is no longer changing down the axial direction. Okay, so whatever velocity, we're gonna get an equation for the velocity at some point. That's not going to change no matter what point in the cylinder that you're at. So you could be at the beginning of the cylinder, at the end of the cylinder. It doesn't matter. All right, and so this is mostly a consequence of the rigid walls. If we were looking at a flexible wall or a deformable wall answer, the biggest difference there would be that we can't assume UR is 0. Okay, and so you would have two components of velocity, both UR and UC. Okay, because that UR component, that's the one that's actually going to be going to inflating the vessel walls or deflating. Okay. And so you can see how that kind of complicates things quite a bit. So, solving for two components of velocity is actually exponentially more difficult than just one. So we're going to assume that it's zero for. All right, any questions on this result so far? Okay, so that's the conservation of mass. So that's all good. Now let's look at the momentum equation. All right, remember, since our velocity here is a vector, technically we have three momentum equations. We have a momentum equation in the z direction, momentum equation in the r direction, and momentum equation in the theta direction as well. Okay, so there's technically three of these. But because of our 1D flow assumption, we know two of those are going to give us a trivial result. So there's no need to write out the equation in the r or the theta direction. Okay, so this conservation of momentum equation is strictly in the z direction only. Okay, so let's write out the terms for that. So we have partial uz partial t plus ur partial uz partial r plus u theta over r partial uz partial theta plus uz partial uz partial z. Is equal to minus 1 over the density rho times partial p partial z. Okay. Remember that partial p partial z, that is our pressure gradient. Plus gz. So gz there is the gravity in the z component. Plus mu over rho. So we have our viscous terms here. So we have our dynamic viscosity divided by the density multiplied by quantity. 1 over r partial partial r partial uz partial r plus 1 over r squared partial squared uz partial theta squared plus partial squared uz partial z. Right. It was already scary in Cartesian coordinates, but it's even scarier in cylindrical coordinates. Couldn't even fit it all in one line. Okay. So let's go ahead and let's start canceling terms in this expression here based on our assumptions. Okay. And the good thing is that the majority of these terms are going to cancel out. Okay, so let's start with the unsteady terms. We have partial uz partial t, right? We already know that we're making the steady state assumption. So this one's going to be equal to 0. Okay. Next, we have ur times partial uz partial r. Okay. We know that ur is equal to 0, so this one's also going to be 0 as well. And actually, let me write down all the assumptions that we're using to cancel these out. Okay. All right, this next term also is going to be equal to 0. And the reason for that is because we have u theta there. Okay. So we already know because of the 1D flow assumption that u theta is equal to 0. Okay. And so we take 0, we multiply that, we get 0. This next term also is equal to 0. Okay. And the reason for that is the continuity equation, right? And so the reason for that is boxed right above this. And so we know that partial uz partial z is equal to 0. And so if we look at that term that we just crossed out, we have exactly partial UZ, partial Z. Okay. That one is 0. All right, next we have the pressure term. So the pressure term is going to stay there. That's the only term we haven't canceled yet. Okay. Next we have the gravity term. So I think this was assumption number 4. We were going to ignore gravity, so we can get rid of that one. Okay. Okay, then we jump inside the viscous term. That first term there is everything looks fine for that. Okay. The next term is going to be equal to 0 because of the axisymmetric assumption. Okay. Remember, because any derivatives with respect to theta, we're going to set it equal to 0. Okay. And then finally, this last term is also going to be equal to 0 because it has partial UZ, partial Z. So this one's 0 because of continuity. Okay. It's a second order derivative, but if the first order derivative before that is equal to 0, taking another derivative with respect to Z is not going to help at all. And so it's still going to be 0. Okay. All right. Wasn't that satisfying? Start with that huge equation, just cancel out just all those terms because of assumptions. It's my favorite part of fluid mechanics. Okay. So let's see what we're left with here. And so on the left-hand side of the equation, everything's 0. So let's set that left-hand side equal to 0. Okay. We still have our pressure term. So we have 1 over rho, partial P, partial Z, okay, plus mu over rho times 1 over R, partial R, times R, partial UZ, partial R. Okay. All right. And so through all that hard work, we've simplified this equation significantly. In fact, we only have one more unknown variable here. The pressure gradient, partial P, partial Z. Remember, we're assuming that to be constant, and so we're not going to consider that in our integration. And so our only independent variable right now is R. Okay. And so in fact, we can change all these partial derivatives to regular derivatives because we only have one unknown remaining. It's a minor thing, so you can leave them as partial derivatives, but technically speaking, now they're regular derivatives. Okay. One small simplifying step. So we can see that we have a 1 over density on both terms, so we can just multiply the whole thing by density and just cancel that out. Okay. All right. And so now that we're here, now that we have just one unknown variable remaining, just R, we can integrate this. Okay. We can integrate this and solve for UZ. Okay. So we're going to perform integrals with respect to R in order to get there. All right. Any questions on this so far? Okay. All right. So let's go ahead and do that. All right. So we want to get this into a form that we can integrate. Okay. All right. So first thing I'm going to do is I'm going to take the pressure term and then move it over to the other side of the equation, just so that we can kind of get rid of that negative. And so we have partial P, partial Z is equal to mu over R times d dr of R duz d R. Okay. All All right, so all I did was I just moved that pressure term to the other side, and I took out the densities from our expression as well. Okay. All right, we want to isolate DDR on one side. Okay, so we want to isolate DDR on the right-hand side so we can integrate. And so as long as that mu and r are there, the mu is fine. The mu is just a constant, but we need to move the r to the other side. Okay. So let's multiply this entire expression by r over mu. And so you have partial E partial Z times R over mu is equal to dVr of R du Z dr. Okay. Now we can integrate this with respect to R. Okay. And so if we integrate with respect to R, that's going to cancel out the derivative on the right-hand side. Okay. We're going to integrate dr, integrate dr. Okay. So this dr is going to cancel out with that. Okay. It's not that it's a fraction, you know, and in fact, I think a few mathematicians might have rolled over in their grave with me canceling out like that, but that's how I think about it. Okay. All right, so on the left-hand side, we're integrating partial p partial z times r over mu. Okay. The only thing that depends on r in this case is just r itself. Okay. So the partial p partial z and the mu are effectively constants, and so they're just kind of traveling along with the ride. And so on this side of the equation, we have partial p partial z times 1 over 2 mu r squared. Okay. Because when you integrate r with respect to r, you get r squared over 2. Okay. We're going to add our arbitrary constant because we're doing indefinite integrals. Okay. And so our solution for an indefinite integral, our solution is only valid up to an arbitrary constant. So we're going to add our C1. Spell. And on the right here, that's going to cancel that outer derivative. And so all we're left with is r du z dr. Okay. We need to integrate this one more time because we need to isolate uz. Okay. But same thing we did in the first step here. We have to isolate the derivative by itself. So let's divide both sides by r. Okay. And so we do that. On the left-hand side, we have partial p partial z times 1 over 2 mu times r. Okay. So one of the r's is going to cancel out with the r's on top. So it becomes just an r. And we have C1 over r is equal to du z dr. All right, so now that we're in this form, we're ready to integrate. So let's integrate this one more time. Okay. So once again, on the right-hand side, the drs are going to cancel out. And so all we're left with on the right-hand side is just uz of r. Okay. So that's what we want. We found our velocity field here. So we found uz as a function of r. All that's left is just to evaluate what's on the left-hand side. Okay. All right, so first we have partial p, partial z. Okay. We're integrating r again, so it's going to be a 1/2 r squared. Okay. There's already a 1/2 there, so we take 1/2 of 1/2, which is 1/4. Okay. So you have 1 over 4 mu r squared. Okay. we are integrating C1 over R. Okay, integral of 1 over R is just a natural log. So we have C1, natural log of R. And we can't forget our second arbitrary constant because we formed another integral, and that's C2. Right. So that's our general solution. We're not at the full solution yet. We need to find out what C1, C2 are. But this is kind of a good break. All right. Any questions on this? All right. All right. So let's solve for C1, C2 because we're not quite done until then. And if you recall, not just fluid mechanics, but just differential equations in general, the way that we solve for these is through applying boundary conditions. Okay. Which begs the question of, what boundary conditions can we apply in our flow? Okay. So boundary conditions are basically expressions of, what the solution looks like at particular location. Usually these are kind of key locations within the flow or key locations in your system where you can define with certainty kind of what the solution looks like. Okay. And we use that information to kind of narrow down our general solution. All right. So we need two boundary conditions because we have two unknowns, right? Let's start with 1 and 2. The first one is fairly obvious. The first one is our no slip boundary condition, which basically says that any fluid that's in contact with the solid wall has to match the same velocity as that solid. Okay. We only have one solid wall here, so we only have just the outer surface of the tube. Okay. And we know from our assumptions that that is a rigid tube. Okay. So what this means is that if we evaluate the velocity at r is equal to big R, okay, so we said we evaluate this at the outer edge of the tube, this is going to be 0. Right. The second boundary condition is actually very interesting. Because when you have cylindrical coordinates, there's only one radius. And so, there's the fact, even though we're in 3 dimensions, the velocity at the outer radius only gives us one boundary condition. Okay. So our second boundary condition here is actually going to be our what I call the center condition. Where we're going to make a statement about what the velocity is going to look like in the middle of the tube, the middle of the vessel. Okay. So you may be wondering, how are we going to do that? Because that depends a lot on the pressure gradient. That depends a lot on how big the vessel is, and so on and so forth, right? So we're not able to comment, or we're not able to set a condition on what the velocity itself looks like, but we can say something, right? And that's something that we're going to say is that we're going to assume that in the middle of the tube, our velocity is going to reach a maximum. So that's a relatively reasonable assumption because if we look at our first boundary condition already, we know that, at the walls, our velocity is going to be 0. Okay. And as we kind of stick around that wall, right, the velocity is going to slowly kind of ramp itself up from 0. And so at the point or at the location where we're furthest away from the walls, which is the center of the vessel, it makes sense that our velocity would reach a maximum at this time. Okay. And what does that mean mathematically? That means if we were to take the derivative of our velocity with respect to r, okay, this would have to be 0. Okay, because we know that whenever we have a maximum or a minimum, the derivative of that function at that location is equal to 0. Okay. All right, so let's apply these two boundary conditions. So I'm actually going to start with condition 2, just because it kind of simplifies things quite a bit. All right, so we're going to take du dr. Okay. Luckily, we have an expression for that already. It is this one right here. Okay. And so you can take our final result here, you can take the derivative, but by solving Navier-Stokes, you obtain du dr already. Okay. So we know that du dr is equal to r over 2 mu partial p partial z, okay, plus c1 over r. Okay. And so if we evaluate this at r is equal to 0, sorry. So we're going to evaluate this, we're going to plug r is equal to 0. Okay. What we get is du dz, or du dr, excuse me, is equal to 0 divided by 2 mu partial p over partial z plus c1 over 0. Okay. All right. So this expression here should raise some red flags because we have c1 divided by 0, and anything divided by 0 is infinity. Well, we think it's infinity, but we don't really know for sure. So this term here is problematic. Okay? Because we can't have anything divided by 0. Okay? And so in order to satisfy this condition right here, and so in order for the derivative of the result to be equal to 0, right? This term that I've circled here just can't exist. Okay. And so kind of the easy way to say this is that in order for this to work out, C1 must be 0. Okay. But that's not 100% satisfying for me because then you have 0 over 0. Okay. And so, I take it an even step further. So what that tells me is that the C1 term, it just does not exist. It just can't be part of the solution at all. Okay. So we're just going to just excommunicado the C1 term. Okay. All right. So that's good for us. And so, even though we got a weird result, it makes our lives easier because we got rid of one term. Okay. All right. Any questions on that boundary condition that we applied there? Okay. All right. So let's go ahead and apply the other boundary condition. The other one's a bit more straightforward. And so we have uz at r is equal to big R has to equal 0. Okay. And so let's go ahead and plug this in. And so when we plug in big R for middle R, we get big R squared divided by 4 mu partial p partial z plus c2. Okay. All right, and so this is a pretty easy arithmetic here. So we're just going to move this term over to this side. And so we get C2 is equal to minus R squared minus big R squared over 4 mu partial P partial Z. Okay. All right, and so let's go ahead and plug that in. And then we get our final solution here. So our final solution, uz of R is equal to 1 over 4 mu partial P partial Z times little r squared minus big R squared. All right, so that is Navier-Stokes and cylindrical coordinates, and so you know that's um that solution there. Any questions on how we obtain this here from that whole solution process? Okay, so a couple of things to note about this solution then. And so one thing that should jump out at you already is the fact that we have a quadratic solution, okay? And so the fact that we have an r squared here means that this is the geometric shape here is a parabola. And so what we say is that this has a parabolic profile. And so if we were to plot this, at any given point within the vessel here, our velocity would look something like this. So it looks like an inverted parabola. We have a maximum at the middle, and then it decays down to 0 near the edges. All right, so that's the velocity field, and so that's kind of what we were hoping for the last 2 class sessions, and now we have it. Okay, so now that we have this velocity profile here, or this velocity distribution, this velocity field, we can do things with it. So we can actually take this result and compute a lot of really interesting quantities. All right. So one thing that we can compute that's very often quantified in cardiovascular health is the volumetric flow rate. Okay? And so the volumetric flow rate, what that is, it's the rate at which volume of fluid passes through the cardiovascular system or passes through a tube at any given time. Okay? The SI units for volumetric flow rate is a volume per time, so it's meters cubed per second. Or more commonly, what you'll see in the cardiovascular system, because it's a lot smaller, you'll see milliliters per second. Okay. So it's a volume over time. So this is really important in cardiovascular health, because if you can compute the volumetric flow rate, that's the literal rate at which your entire blood volume is pushed through your entire system. And so it's a metric of kind of how strong your heart is. So the stronger your heart is, the more muscular it is, the more it can kind of push all this fluid through your system. And the faster it can kind of push things through, the more easily kind of oxygen flows through your system, the better way the waste kind of gets out of your system. So you want a high volumetric flow rate, okay? But of course, in medicine, they don't call it volumetric flow rate. That's the engineering term for it. And so in doctors, what they call this cardiac output. Okay. So cardiac output is kind of the medical term for volumetric flow rate. Okay. Okay. So we can compute cardiac output or volumetric flow rate from our velocity distribution. Okay. Assuming we just have one vessel. Okay. And a lot of times you'll just hear me call it just flow rate, because volumetric flow rate is kind of a mouthful, but flow rate is kind of the other term for it. Okay? So the way that we can compute flow rate is by integrating our velocity field. Okay. And we're actually going to integrate our velocity field over a 2D surface. Okay. And that 2D surface is actually the cross-sectional area of our tube. So the symbol for volumetric flow rate is Q. Okay? And so the way that we compute it is we can integrate with respect to the area of UZ of R, the area. Okay. All right. So we can simplify this, and so that right there is the general expression. But we know our cross section in this case is a circle because we're in cylindrical coordinates. And so if we simplify this a bit more, this becomes a integral or an integral from 0 to big R of UZ of R, okay, multiplied by 2 pi R TR. All right, so that works out a little bit nicer because usually for a surface integral, you have to do 2 integrals here, but we're making use of our circular geometry to cut that down to just 1 integral. Okay. All right, and so what you can do from here is you can take our velocity result, plug in here, and evaluate this derivative, or evaluate this integral, excuse me. I'll spare you the details. In fact, the details of this integration is one of your homework assignments. And so, plugging in that velocity distribution and carrying out that integral, that is the last problem on the homework. Okay. But I will give you the result. So just so you can check your answer. Okay. And so if you run through that integral, what you get is minus pi r to the 4th, big R to the 4th, divided by 8 mu times dp dtz. All right. So one of your homework problems is to verify that result right there. So if you plug in the velocity distribution, you integrate it, you should get that result. Okay. All right. Any questions on this so far? Okay. All right. So let's actually take this result here and let's put it in a different form, just because we're going to need it in the next section. Okay. If you remember kind of when we started today, what I told you was that the pressure gradient here, we can plug in for it using this expression here. So we have P1 minus P2 divided by L. Okay. If we change P1 to P1 minus P2, we call that delta P. So that delta P is just a change in pressure. We can kind of come up with another expression. Okay. All right. And so what we have here is we have Q is equal to I'm sorry, there should be a minus delta P. Okay. So we have a minus pi r to the 4th divided by 8 mu times minus delta P divided by L. Okay. So all I did there was I plugged in for the pressure distribution and I forgot that negative for the delta P, okay? All right, because what we want is we want these negatives to cancel out, okay? And we're going to take this and solve this expression for delta P. Okay, we have delta P is equal to 8 mu L divided by pi r to the fourth multiplied by Q. All right, and so what we have here, and the reason we did this is that this is the relationship between pressure drop and flow rate in a tube. Yeah.
Is that P1 minus P2 minus delta P, or is it P1 minus P2 times negative? delta P?
So that's P1 minus P2 is equal to minus delta P. Yeah. So actually delta P, its exact definition is P2 minus P1. So P1 minus P2 is minus delta P.
Okay.
Yeah.
Those are just plus signs on the next step, right? Those little-
Yeah. Yeah. So because there were two negatives, and so I just canceled them out. All right. So that was a lot of fluid mechanics, and so this was kind of a crash course in it, right? And so it's like we're back in 333. But what's really fascinating about these results, and kind of the reason why I kind of went through all of this. I mean, part of that was just to review these concepts, just so that they're in your mind. But already, we can take these ideas and we can take these concepts and actually apply it in a really interesting way to the cardiovascular system. Okay. And so that application is a concept known as Murray's law. And Murray's law is an idea that talks about how blood vessels actually bifurcate. Okay, so this is Murray's law for bifurcating vessels. Okay. So first, let's define what a bifurcation is before we can talk about how fluid mechanics kind of factors into it. Okay. One common thing that happens a lot in your cardiovascular system, and this is mostly just so blood can get to where it needs to be in the most efficient way possible, is you're gonna have blood vessels that split into two or more different paths. And so it looks something like this. So we have one vessel coming in, okay, and then it'll reach a point where it needs to split into two. And so it looks just like that. So the flow is coming in from the left, and it exits out the two vessels on the right. So this vessel right here, this is known as the parent vessels, or the parent vessel in this case. Okay. And then the two vessels that kind of spawn from it, don't ask me why it has this name. I guess, only blood vessels can only be female. And so these two vessels that come out are the two daughter vessels. So this is daughter vessel 1. And daughter vessel 2. I literally spelled it right above and then spelled it wrong down here. Okay. All right. So this needs to happen a lot in your cardiovascular system, because if you can imagine, if you had just one blood vessel that ran through your entire body, right, just one singular path, it would take forever, and it would take an immense amount of energy to drive blood through that entire system. Okay, it would be the same thing as if you had just one freeway that went through all of Southern California, so just one road. You can give that road 20 lanes. I don't care. It's going to take you forever to go from one part to another. Okay. And so in order to make the pathing more efficient, bifurcation has to happen a lot in your system. Okay. All right. What's interesting is that if you look at the sizes of these vessels, okay, and so we'll call the radius of the parent vessel, we'll call that RP, and we'll call the radii of the daughter vessels, we'll call that RD. Okay. The daughter vessels don't necessarily have to have the same radius, but we're just going to assume that it is for now. Okay. The interesting thing is that we want to know is that is there a relationship between the radius of the parent vessel and the radii of the daughter vessels whenever a bifurcation occurs? And you'll be surprised to hear that there's actually a physical fluid mechanics reason for these vessels to have a certain size. And that's mostly just to maximize energy efficiency. Okay. All right. Okay, so to kind of understand this, or to give this a bit more context, let's talk a little bit about what happens when let's talk about kind of the factors that affect how much energy or how much power it needs to drive blood through your system. Okay. Okay. Because just because we know from intuition is that if you have a tube, okay, and you want to drive flow through that tube, it's going to take a certain amount of energy, right? You experience this every time you drink a drink through a straw, right? And so in order to get the drink from your cup into your mouth, you have to apply energy from your lungs. Okay. And so there are certain factors that affect how much energy that you have to output in order to drive that flow. Okay. And in particular, since we're looking at the radius of these vessels, let's look and see how these factors change as the radius changes. Okay. All right. So first factor to consider is the viscous shear stress, or the friction in the flow. Okay. So as the radius decreases, okay, and so as your tube gets smaller and smaller, right? The amount of power and the amount of energy that you need to overcome friction or viscous forces will increase. Okay. And so intuitively, if you think about it, if you've ever tried to like squeeze, a fluid through a very small opening, is that as that opening gets smaller and smaller, it gets harder and harder to squeeze that fluid flow, especially if you want to increase the amount of flow. Okay. And so as your radius gets smaller and smaller, it becomes harder and harder to overcome those viscous forces. Okay. On the other hand, so we know that if we decrease the radius, it's going to increase our work, right? On the other hand, as the radius increases, this will also increase our amount of work, okay? But for a different reason, okay? And so as you increase the radius, we're assuming that blood is completely filling this tube. So we don't have no empty pockets of airspace, okay? And so as your radius increases, this just increases the amount of mass or the amount of blood, the amount of volume that you have to kind of push through. Okay. And so like we talked about on Tuesday, every piece of mass in the world has inertia, right? And so if you're increasing the amount of mass, you're increasing the volume, then inertia is going to increase as well. All right, and so it seems like, no matter which way we go, we either increase our radius or decrease our radius, we're kind of screwed in a different way, right? But what this kind of implies is that, we have two competing factors here. And whenever you have two competing factors in math or physics or engineering, that means there must be a happy medium in between, okay? And so that happy medium is basically outlined in Murray's law, okay? And that happy medium is going to tell us, if you have a parent vessel of a certain size, then the daughter vessels are going to be a certain size to kind of balance out this energy requirement, okay? All right, but we'll go over that on Tuesday because we're out of time for today. Any questions on this before we wrap it up for today?
Just general assumption, would it just be half? Would each of the two bifactors be about half the radius of the original?
You would think so, but if you did that, then you would have kind of what's called an area conserving situation. But that's not necessarily the case. That's not the most energy efficient because these two quantities here, they scale differently. So we'll see. All right, so that's all we got time for today. So thank you guys for coming. On Tuesday, we'll pick this up and we'll kind of finish up our derivation of Murray's law and see what that means for the daughter vessel radius. Okay, and then we'll go over a few more applications before moving on to the next. All right, so thank you guys for coming today. Hope you guys enjoy the rest of your day. Hope you guys have a good weekend. Stay dry. I heard the rain is only going to get worse over the weekend, so take care of yourselves. And I will see you guys next week. Thanks, Bob.
Well, like you said,
Your pressure.
The slopes of those, they're probably like you graph it. The slope of that. Would that be an indicator that the
That's a good question. So that term does serve as well, but that serves as that natural long-term. So the fact that we go all the way to the middle, then that term just can't exist. It's a weird kind of singularity. That has to do with the assumption or. I haven't checked the wait list, but let me see. I don't know if anyone's dropped those.
Do you remember what the ad date?
It's Monday. Last week.
It takes time.
I don't know, some people might be scared off with have your scopes. So we have. So there's 34 people. I think some people may not have used their permits.
So is there a chance that we can email them?
Well, you're still 6 on the wait list, so, but, yeah. So I know Tamid, I know he's on Zoom. I know Nawaz on Zoom, so I know these two are participating.
Dylan's not in the class. I think he forgot to drop.
Dylan Gomez, he told us he was gonna drop the.
Oh, really? Okay. I'll see where it is on Monday, and then if it's, then I'll have them issue a permit.
He might have forgotten to drop it.
Yeah, because I don't think I've seen Andre, I haven't seen Kelvin. Yeah, and yeah, if Dylan's dropping the class, then that would make you next up, so.
What if I just stayed and then did all of the work and then chose the department?
Oh, yeah.
Well, they're trying to cut, so that would be a retroactive, so they're trying to cut down.
Yeah.
Yeah, we'll see on Monday, because if these 3, I know these two are, I just need to follow up with them to get their permits. And then after that, there's one more spot, and then.
Please. Yeah. Thank you. I
Yeah.
really appreciate it.